This is the 3 o'clock talk on Sunday. Up next is a fresh look at SELinux with Daniel Walsh.
Okay. Hey. Okay, thanks for having me. I just wanted to, a lot of times I'm going to go through SELinux. I'm going to try to teach you, if you've had SELinux taught to you before, I often think it's taught at a way too difficult a level, and so I'm going to try to go through it at a much lower level. We're going to use the coloring books. Sadly, I ran out of coloring books for everybody. But about a year and a half ago, I heard about this bash exploit. And so I quickly wrote a blog, quickly did an investigation to see what SELinux did about the bash exploit. And later that day on the ride home, I was listening to NPR, and they came up and they talked about shell shock. And I said, what the hell is shell shock? I had no idea what it was. And after writing this article, so if you see this article, it's actually talking about shell shock, but I called it the bash exploit because whoever adds cool names to exploits had not reached me yet to tell me that they renamed it. So an interesting thing with shell shock. So shell shock instantaneously made every single web server in the universe that did bash, ran bash or CGI scripts, was vulnerable. It could be totally taken over, every single web server in the world. The only thing to stop that exploit was SELinux. Okay? So the day it happened, any machine that was running with SELinux in enforcing mode blocked it. How many people in this room were running the I'm not going to ask because I hate to see the answer. Okay? But that's the power of SELinux. Okay? SELinux is not catching known problems, no, not necessarily catching known problems, it's catching the unknowns. Okay? So SELinux puts everything into a box and controls it. We're going to talk about that a little bit later, but I just wanted to point this out. We're going to talk a little bit about virtualization, multi-tenancy, and some of the stuff. So, for those of you who don't know who I am, I used to call myself often Mr. SELinux. So I started at Red Hat 15 years ago. At the time, I have a security background. I worked way back on a Project Athena, Kerberos. I worked on VPNs back when VPNs were just being created, firewalls. I worked for Digital Equipment Corporation. Worked on the first firewall at the White House, by the way, whitehouse.com. Whitehouse.gov. Whitehouse.com was a porno site. Okay. Yeah. I remember seeing Hillary and Bill on it one time. Yeah. Anyway, so 15 years ago, the NSA came to Red Hat. 15 years ago, I started working at Red Hat just before 9/11, to give you an idea of how long ago it was. And a couple of months into my term, about 6 or 7 months into it, the NSA came to Red Hat and asked, the seats up front here, if everybody wants to squeeze in, came to Red Hat and said, we have this really cool new security mechanism that we really need to get mainstream, so we want to work with you guys to get it into the upstream kernel and everything else. So people went around Red Hat and looked for anybody that had the word security in their resume. My name popped up, and I became the SELinux guy. So for the next 10, 11, 12 years, however it was, I worked on SELinux. Okay. I also worked on a thing called namespaces. So in RHEL 5, we introduced the concept of namespaces, which was PAM mount namespace. The mount namespace was introduced for a thing called MLS. So SELinux allowed us to get to MLS, multi-level security. We're going to cover that a little later, but we actually introduced this concept of the mount namespace. Eventually, the namespaces grew into a bunch of other namespaces. So I am now the head of container technology at Red Hat. So I have the Docker team underneath me. So we submit patches all the time to Docker, and I'm constantly fighting with them to get my patches accepted. But that's what I do now. I also did the Docker part of SELinux. So let's get into, but you're not here to hear my history. Let's go in and look at that. So I call this topic, I actually combined two different talks here together, and I'm not sure we run out of time. Are we the last talk of the day? Oh, shoot. Okay. I was hoping to go over. I can go 30 minutes over. All right. So they throw me out. Okay, so SELinux, when you get an SELinux error, it's trying to tell you one of four things. And that's really what a lot of what this talk is going to be covering. And so you have something wrong with your labels. You change your file system's default and tell SELinux about it. Applications or SELinux has a bug, or you've been compromised. Now, that's really the only thing it's going to tell you. The problem is trying to figure out which one of the four it is and how to react to it when you get one of those. So let's so the most common error for SELinux is you have something wrong with your labels. So everyone please stand up. This is the interactive section. Everybody's ever seen me, they've had to do this before. I make everybody do this every single time. Okay, you're going to read the screen, okay, in unison. This is the Church of Dan Walsh. Ready? Yeah, you don't have to do that one. Okay. That's it. Everybody knows what SELinux is. Okay, sit down. So SELinux is a labeling system. Okay, simple as that. I don't want to talk about. We're going to cover some other deeper topics in it, but it's a labeling system. If your labels are wrong, things are going to blow up. Anybody see the canonical talk yesterday, the keynote? Okay, he put up a slide that I would love to steal, but he probably won't let me. And he put up the way the Linux operating systems evolved over the years, or actually Unix has evolved since I was, a youngster. In that we have applications, they look like amoebas, right? So you install them, and these applications can be configured 100 different ways. Okay, so you have the Apache web server. How many different ways can you configure Apache? It's basically 1,000, millions of ways, right? And then you have databases. They can listen on network sockets. They can listen on local sockets. You can change the socket. So you can change all this configuration. And then we have to throw in other applications. MariaDB, slightly different from MySQL. So there's constant change in the operating system. And SELinux wants to control all of that. So if you install and reconfigure anything in SELinux, you have to fix the labels. Okay, let me tell you about another labeling system that no one in this room probably thinks about. Discretionary access control. Does anybody even know what that term means, discretionary access control? Okay, about half of you do. Now let me tell you what it is. Ownership, permission flags, read, write, execute. Okay, that's what's called discretionary access control. So I have, every process on the system has what? An owner and a group. Right? It actually has an owner. So there's an owner or a process. Every file system object has a label on it. The label is the ownership, the owner, the group, and the read, write, permission flags. So if you get permission denied anywhere on the system, the first thing you do is you go and fix the labeling system. It just happens to be the labeling system you are familiar with. So you're going to go in and say, Apache got permission denied. Let me make sure the file's owned by the Apache owner. Let me make sure that the search path has proper rights the Apache owner can search through it. Okay? At which point, you run it, everything looks good, you run it again, it blows up, and at which point you say SELinux sucks. Okay? And that's what you guys all do, because you don't think about fixing the labeling from an SELinux point of view. Tom Hayden. Everybody's seen this before? This is actually a website, stopdisablingselinux.com. It's done by Major Hayden. He's one of the top security guys at, mental blocking is the name of his company, Rackspace. So he put this up. He's a good guy. And he actually gave me the Set and Force 1 shirt. So here's a real world example. This actually happened. The guy in the next cube for me had an egg dispenser. What does this egg dispenser dispense? M&Ms. Someone put Skittles in the M&Ms dispenser. Okay? Talk about permission denied. That is, I hate Skittles, okay? And he wanted this slide going up. Okay, so everybody get out their SELinux textbook. You can start looking through it. This textbook, the SELinux coloring book, is probably the best document I believe ever written. So you can go out to Amazon on SELinux. You can go out to Amazon, buy those big thick textbooks, or you can read this, okay? And you will have an understanding of SELinux. You can also, for those that are not in the room, it's available on the internet. One of the reasons people really like it is Maureen Duffy does she works for Red Hat as actually all sorts of UI stuff. So you can get this and print it out. We've given out hundreds of thousands of these. Probably not hundreds of thousands, but thousands. And actually, interesting story. Any Japanese in the room? Okay, when we gave this out, Japanese Red Hat came to us and said, can you make it a comic book because Japanese people don't know what coloring books are? Is that true? I said, that sounds like the stupidest thing I've ever heard of. But anyways, they wanted it, so I told them to color it in themselves and call it a comic book. But okay, so SELinux is a labeling system. If the labels are wrong, SELinux will generate errors. Solution, fix your labels. I stopped myself. Okay. Okay. So we're going to talk a little bit about the labels now. So we're going to go a little. This is where we're dropping down a level, and this is going to cover the coloring book. There's two types of enforcement that SELinux takes advantage of. The first one we're going to talk about is called type enforcement, and this is where we really define the type. You're an Apache process, right? So if you look at the SELinux label, it's kind of ugly looking, but there's user, role, type, and level. And we're really talking about the third field after the colon, and this is the type field. But every process on the system has a type. When I log into a system, most people log in as administrator, they're unconfined T. That's the unconfined type. You're able to do anything you want in the system. But if a process starts as a system process, like Apache, that's going to run as the Apache type, which is HTTPD_T. When the shell shock happened, if the shell shock person logged into the system, he was running as HTTPD, actually is a CGI script, which runs as HTTPD CGI script T. So when the CGI script was running bash, the way bash exploit worked is you were able to say something, you were able to pass something to the end of the bash command, or the end of the CGI script, that the bash command would then execute. So when SELinux saw it, the CGI script came up and said, hey, I want to look at users' home directories. And SELinux stepped in and said, no, you're a CGI script. You're only able to do CGI things. And said, hey, I want to try to run sudo. No, you're a CGI script. You're only able to do things with CGI script. Had nothing to do with permissions, nothing. You could have world-readable files on the system, anything. SELinux would block it. So there's the standard type for Apache web server. And here's the content type. An interesting thing about SELinux that people that start to struggle with it often think is that if I have the type of the process, I want to assign it to the type of the file, right? So you don't assign process types to file types. So there's a separation. You have a process type and you have objects, data objects. So this is the type that Apache is able to write to. Most types are read-only. So most types that Apache is allowed to read to are read-only. But let's take it back a step. So when we look at type enforcement, let's look at a simple example of a cat and a dog. So I have a type, and I say this is a cat type. And then I say this is a dog type. All right, these are processes on your system. And then we have objects on the system. We have cat chow, and we have dog chow. Okay, so those are objects on the system. Then I write a rule to the policy engine, and this is exactly what the policy rules would look like. Okay, this policy rule says allow the cat process to eat cat chow food. Okay, so food is like file, directory, whatever, but basically it's a category of the object. So we write thousands of these rules that says allow cat to eat cat chow, allow dog to eat dog chow. SELinux system, like all firewall rules, is deny by default. If I don't have an allow rule on the system, you are not going to be allowed to do it. The process is not going to be allowed to do it. So the cat's able to eat the cat chow, the dog's able to eat the dog chow, the cat's able to ask the kernel for more cat chow, but when the dog tries to eat the cat chow, the kernel steps in. Any questions? Okay? That's what type enforcement is. It's that simple. It's type enforcement. Okay? We're going to get a little bit further into this. So SELinux labels. Now we're going to cover, so that's the standard way we protect systems. Now I'm going to put on my other hat. So type enforcement works real well for use cases where you have like an Apache server and you have a Apache data, or you have a database server and you have database data, and you have home directory data. Where it doesn't work well is what I call multi-tenant systems. Okay, multi-tenant systems are things like Docker, containers, VMs. Okay, we're going to show you OpenShift in a second. So there's lots of use cases where you're going to have hundreds of VMs, or VMs running on your system, and you want them, that's a VM, and this is VM data. But what I want to do is I want to make sure VM A is not able to read VM B's data. Now I could create all these types, but all of a sudden I have thousands and thousands of types. So what we needed is a different types of security for the system. So this is back in SBIRD, probably around 2008 timeframe, we invented the concept of what we called MCS separation, or SBIRD, secure virtualization. Secure virtualization, by the way, give you an example where SELinux is ruled. There's been 2 breakouts of KVM on RHEL systems over the last, I don't know, 6, 7, 8 years. There's been 2 breakouts through the KVM. So if you have a process running in a VM, the process breaks through security on the VM, then it breaks through the hypervisor and actually gets control of the host system. So that's the object of any hacker that's running in EC2 right now, is to get to that point, because then you can take over the universe. There's been 2 known breakouts, 2 known vulnerabilities in that. Both of those were blocked by SBIRD. SELinux controlling what's going on in the system. All right, but let me go a little further into what this type of protection is. So we can identify everything as a Docker type, or as an OpenShift type, or as a VM type, but we have to have some other piece of data that gives us separation. So an SELinux system has this 4th field called the level field. Anybody in here ever do anything with trusted systems? All right, just 1 or 2, 3 people. So things like Trusted Solaris or SELinux all the way back since RHEL 5. The concept was this multi-level system where you would have a top secret process and a secret process. And there's rules that were written many, many years ago, back in the 1970s, that said a top secret process can read secret data, and a secret process can write top secret data, but a top secret process cannot write secret data. Pretty strange rules, right? But that's what MLS, standard MLS, so that's not really totally the way they work, but the idea was that if I have a secret process running a secret process reading secret data, I don't want that secret process to be able to write non-secret data, okay? That is the WikiLeaks stuff, right? I don't want to take the top secret data and let it get down to secret. So that's why top secret processes can't write secret data. Similarly, the other one that's weird is that a secret process can write top secret data. And that's, I always equate to the soldier sees the tanks over the hill, and he's going to tell the commander that this tank's over the hill. So he's actually writing data that he might be only secret, but when he tells the generals, all of a sudden it becomes top secret data. That's the basic idea. So anyways, the problem with MLS, which we introduced in RHEL 5 back in 2006, is that almost nobody in the universe, other than the military, sets up their systems to run that way. So we had this 4th field that we weren't taking advantage of. So most targeted systems we've played with SELinux has that as S0. So we decided to take advantage of that. We made a new thing called MCS, which is multi-category security. And what we did is we basically allow us to assign sort of random labels here, and the rules basically say that that random label has to match. So if I have a process that has a label of S0, C1, C2, I have to have an object in the operating system that has the same label. And that's what SBIRD is. So let's go look at it. So SBIRD, if I'm running a virtual machine, it's going to run as the SBIRD type, and then libvirt, the tool that launches virtualization in KVM, will pick out a random MCS label and assign it to it. Then it will pick out a file in the file system, assign the same label, and then basically the kernel will say that these 2 have to match, otherwise you're not going to be allowed to read or write that file. MCS enforcement, so it's multi-category security based on the multi-level security, which I went over pretty quickly. And now we're going to go through the next chapter of the SELinux coloring book to cover MCS security. So in this case, we have 2 dogs, right? So they're both the dog type, but what we want to do is we're going to assign a random label. In this case, it's not so random. We're picking a name, but it's Fido and Spot. We're going to now use our example of dog chow for both of them, but now we've added an MCS label part of the dog chow. So we've said that that's going to be Fido, and this dog chow is going to be Spot. And if Spot's eating, in this case, the kernel must have been set permissive because Fido is eating Spot's dog food. So in enforcing mode, Fido would be allowed to eat his dog food, and then if the kernel would stop Fido from eating Spot's dog food. Okay, so that's basic idea of MCS. And now let's go. Okay, MCS enforcement protects liked processes from each other. VMs, OpenShift gears, SELinux sandboxes, Docker containers. I figured this thing out. I've got a big hammer, and all I've been doing is looking for nails since then. Okay, so is everything that is a multi-tenant environment needs this. Rocket now supports this, so if you're using Rocket containers, systemd nspawn supports it. So all these environments support this type of security. The tools that launch the containers, that launch the object, picked out the random labels, assigns MCS label to all content, launches the process same label, and then the tool is in charge of guaranteeing the uniqueness. So Docker has to guarantee uniqueness. Libvirt has to guarantee uniqueness. Rocket, any other tool that's going to do this has to guarantee the uniqueness. So let's take, hopefully this is not too loud.
Today I'm going to demonstrate how SELinux controls what an OpenShift gear is able to do on a system, even if the OpenShift gear becomes root. I start out by showing that my process on the system is running as unconfined T, and I'm about to use runcon to become OpenShift, the OpenShift label. I also show that I'm running as root on the system. So if I run the runcon command here, I'm going to switch over to a label of staff U system R OpenShift T S0:C0, C1. When an OpenShift gear is launched on an OpenShift system, they are always launched with the OpenShift T type. But each OpenShift gear also gets attached to it a unique MCS label. Here it's S0:C0, C1. Is associated with the process. Also, the gear gets its content also labeled with the same MCS label. So now that I'm running as OpenShift T, I'm going to show you that I'm still running as root on the system, but now if I try to cat Etsy Shadow, I'm going to get permission denied. If I try to create content on the system, I'm going to get permission denied. And even if I go into the live OpenShift directory where the different gears store their content. In this case, I set up two directories for my demonstration, one called Gear 1 and one called Gear 2. If you notice, Gear 1 has the MCS label of S0:C0, C1, and Gear 2 has S0:C3, C4. So if I show I'm an OpenShift gear trying to attack another gear, I'm in this case representing myself as Gear 1, I'm going to try to go into the Gear 2 directory and look around. In this case, I get permission denied. But if I attempt to go into my own directory, I can see content in there, and if I want to create new content, I can create it. If I look at the labels on the content that I create, it's all labeled with the MCS label of S0:C0, C1. So now, if I get frustrated with SELinux and I want to turn it off, I can attempt to turn it off with set enforce 0, and of course we're also blocked from being able to disable SELinux on the system. So this demonstration, this little video demonstrates what SELinux can control, what an OpenShift instance is able to do, even if the OpenShift instance somehow became root on the system.
Okay, so to give you an idea, OpenShift, does everybody know what OpenShift is? Okay, a few of you do. So OpenShift is a PaaS server that Red Hat introduced, I think 4 or 5 years ago now. Okay, matter of fact, the guy that developed it was Mike McGrath, who's now works with me in the Docker team. But this is OpenShift v2 that we're demonstrating. OpenShift v3 is going to be based on top of Docker containers with Kubernetes and stuff. But basically, it's going to use the same technology. So OpenShift has sort of taken off. I think they now calculate they have about 2 million users of it. OpenShift is based in EC2 cloud instances. Anybody in the world can get an account there. All you have to do is provide a username and password, or not username and password, provide an email address, and you're able to get an account. We also allow you to have shell access to OpenShift v2 machines. So we give you shell because we figure if we're giving you the ability to build web services on top of a PaaS server, you're going to figure out how to get to shell on top of that system. So right out of the box, we give you shell. We take away no security, no tooling from you. So we allow you to use any tools you want. The only thing we do is we wrap you with SELinux to make sure you break out. Now, we have had over 4 years with 2 million users, we've had no known exploits. Now, maybe the NSA's done something. I don't know. But we've had nobody has broken through the security with a shell account on the system. We also monitor the heck out of this, make sure the kernel's totally up to date, things like that. So the attack vector here would be through the kernel. Yes. because of the NSA? Do you think my answer to that is, if I worked for the NSA and I wanted to exploit all machines in the world, I would not put an exploit into the thing that comes from the NSA. I would have someone get a random email account, give a patch to NVIDIA driver or something like that, and that would be my attack vector. This is open source, right? So it's open source. Everybody in the world has looked at the SELinux code. It's gone through multiple review processes. It's far more likely that they have if the NSA had an exploit, it's far more likely that it's going to do that. So turning off a security feature that has no effect on the kernel, I mean, that's just basically the kernel. You don't know what's going on in the kernel, whether SELinux is enabled or disabled. The code is in the kernel. That to me, I always think is ridiculous. But yeah. That's coming up in a set. That's coming up in a well, the labels are written in policy, so there's policy writers writes. So the policy writers write the rules. I'm going to show you how the labels get onto processes and labels get on. Okay, so when libbvirt launches the virtual machine, it picks out an MCS label to assign to the process. Then it assigns the image the same label. When libbvirt takes down the container, it basically kills the process and then relabels the label on the VM to something that no VMs are allowed to read. So it can change the labels all the time. It just doesn't leave permanent content on it. No. Yep. It's just that those sequence of letters. I mean, there's more to it than that. That those labels in an MLS system mean something. In an MCS system, we're just taking advantage that we have this construct of MCS labeling, and we're just using it. The reason we use two labels, so we use S0. S0 is the sensitivity level. So in an MLS system, you'd have S0 to S15. We only use one sensitivity on the system, and we have 1024 capabilities. So we can use 1024 two-character combinations. Okay, that gives us 500,000 potential unique containers and virtual SPR. So the uniqueness is basically 1024. I mean, it's 500,000 unique VMs you could run in a system. So when we designed it in 2008, we thought that was pretty good, that we wouldn't have a problem. That was before we got the containers. Now theoretically, containers are going to, as we see with OpenShift, they have 2 million users. All of a sudden, we have potential problems with that. But guess what? I can add a third label to this. So I could use S0, S1, S3, and all of a sudden I get another multiple of 1024 times that, minus some numbers. But anyways, it can get huge if we really find that as being a problem. So most SELinux issues are caused by labeling issues. SELinux should work by default if everything is labeled correctly. Sadly, not everyone wants to store their content the way I tell you to store your content. Okay? All right? There's a problem. Every process and object in the machine has a label. If your files are not labeled correctly, access might be denied. Alternative paths to confined domains, SELinux needs to know. So if you want to install your Apache server in some random directory on the system, you got to tell SELinux about it. If you want to move your content, your Apache content, to random directories like /u, I don't know why people like /u, but it must be an old Solaris thing. Or you have /serve or /web. There's certain directories that people put their content in. You have to tell SELinux about it. The way you do it is there's an SEmanage command, which is the SELinux management command, and that's SEmanage file context. So this is basically saying I want everything under this directory to be labeled as Apache content. When you use an SEmanage command to do management, that just tells SELinux what the default should be. It does not change the inodes on the system. I didn't mention earlier that SELinux is based on inodes. So the same way discretionary access works, the label is associated with the inode on the system. All right, it's not path-based, but it gets assigned from a path-based system. It gets assigned to the labels get assigned via the file context file. After I set this, change my defaults, I have to run a command called restoreCon. If you play with SELinux for a while, you're going to get real familiar with restoreCon, because restoreCon basically says change the labels of this file or this directory back to the default. Go read the file context file and change the default. Lots and lots of tools on the system have file context built into them, things like RPM. So when I install a package on the system, RPM will automatically set the correct label. So when I install the default Apache server, it gets installed. So that's how the labeling initially gets created on the system. But if you want to put contents in random directories, you're going to tell SELinux about. So file labeling. So the file context file is stored into this directory, SELinux targeted context file context. So all the labels are stored there. If you want to go look at that file, you're going to see thousands and thousands of regexes that are where we've learned content gets stored. File labels are usually stored as xaddrs, almost always stored as xaddrs. Certain cases, file systems don't support xaddrs, yes. Yes, it performs perfectly, zero performance hit. Is there a cost to discretionary access control? Okay, so it's the same basic cost. Pretty much with the modern Linux, they just did some studies on it. We published them. SELinux has negligible effect. You can set up horrible situations. It's not the labeling on the system that's going to cause it. It's basically the kernel checking access control on there. But the kernel's already going through lots of access checks every time you access an object. So for the most part, anybody that disables SELinux because of performance, unless you're Wall Street trying to get an extra microsecond, whatever, you're fooling yourself. There's so much CPU that it's not really a problem. Yes, I'm never going to get through this. It's going to go about 3 hours. Yeah. Right. Right. So even in that situation, the one place where you, to me, you would have to really worry about is network throughput. So that's where you really need to check because, again, for the situation where you want packets flying as fast as possible, the SELinux system is going to be checking every single packet that comes in. Potentially could check every single packet come in to make sure that it's a secret packet versus a top secret packet. So there are those checks built into the system. So match pathcon is another tool that you can use to figure out what the path is going to be. On the SELinux system, if you played with it, any core utilities, any command you want to run, always look for the -Z. So that's sort of the SELinux flag that tells you what the labels are associated with objects on the system. SEManage context file is used to change the default labeling. And restore command takes the default labeling and applies it to the xaddrs on the file system. So I already showed that. So file labeling. This is so a government entity uses Tivoli. I always change these to protect the innocent. Tivoli stores log files in var IBM Tivoli common cod logs. Anybody have any idea why var logs wasn't good enough for IBM? Yeah, it's this type of stuff that drives me crazy over the years, okay? It's like we'll just pick random. If you ever looked at an Oracle system, okay, so we don't know where Tivoli stores its logs. So someone installs a log package in here. They put the logs in there. They tell the log rotate tools and the log analyze tools that this is there. They forget to tell SELinux about it. SELinux has a problem with logging tools because they run as root. They analyze random code that can be generated by anybody, and then they take actions based on that code. Well, that seems like a good exploit target vector, right? So we needed to have that. I see AVCs on confined domains saying it's trying to access var_t. var_t is the default label of var. We don't have labels for IBM, storing in random locations. I see labels. So how do you figure out what the label of this be? If it has the word logs in there, I instantaneously say, I wonder what the label on var logs is. And I go and look at that, and it says ls is var log, and I see it's var log t. And so I run an SEManage command that says SEManage fcontext add var log t to IBM's weird location for its logs. And run restorecon to set it. I usually go at a fairly global level to run these, but you could have done it down to the path. Problem solved. Default T files. So SELinux knows about all the stuff that's in / that comes from the distribution. Any other crap you put into slash, I have no idea it is, and SELinux has no idea what it is, okay? It could be top secret data. It could be credit card data. So we don't allow any confined domain on the system to look at anything that's in the slash directory that we don't know what it is. Similarly, we don't allow it to look at var t, right? So var t, we don't know what that content is. So you have to tell SELinux if you're going to store content there. So by default, all non-distribution directories in slash will be labeled default T. SELinux has no idea what content is. Yeah, I already said that. So a big retailer moves its home directories to /u/home. This is another Solaris thing, I think. I don't know why /home wasn't good enough for them, but they wanted it in /u/home. So /home, so guess what you're going to label /home as? Anybody know what directory we should look at for this? /home, very good. Okay. So this means all home directory content is labeled as default T. So we have confined domains like SSH-Daemon and Apache that want to look at content in your home directories, and I don't know if it's credit card data, so we block it. We probably want uhome to be the same label as /home directory. So what do we do? Well, one of the problems with just doing what we did with SEManage there is we could probably have multiple labels underneath /home for differences, right? My home.ssh directory is probably labeled differently than my home/public HTML directory. So I don't want to go through and execute the SEManage command 400 times because, so what I do is I can do an equivalency. So the equivalency label says fcontext add, I'm actually doing a regular label here, so I'm doing saying /u. I'm just going to name it the same as /home, but then I do an equivalency. And all this says is -e treat /u/home as if it was under /home. Now when restoreCon u/home goes in and asks the system, it actually asks for /home dwalsh to set the labels instead of /u/home. So it's pretty simple. Labels under all files under uhome as if they were labeled under home. /uhome dwalsh gets labeled as that, and public HTML gets labeled as that. So it'll use the same labels as if under home, and of course you have to run restoreCon on it. So a common problem, creating content in my home directory and then I move it somewhere with the mv command. Everybody knows the rule about the mv command when you move content, right? It maintains the security attributes of the object that you're moving to the new location. Right? When I move a file to a root system, it does not change from dwalsh to owner root. It stays as dwalsh. If I copy a file to the slash directory and that file does not pre-exist, and I'm running as root when I copy it because I wouldn't be able to do it as dwalsh, what happens to the security attributes of the file I create? It's owned by root. Okay? So guess what? When I move an object on the system from, say I'm creating index.html in my home directory, which is user home t, it's user home content, probably where I store my credit card data, and I move that index.html to var www.html, it maintains the security attributes that it's dwalsh, and it maintains the security attributes that it's user home t. So now I go and run Apache. Apache gets permission denied. I go and say, oh, I forgot to change the ownership to Apache. I changed the ownership. I run Apache again, gets permission denied, and what do I say? SELinux sucks, okay? Follow me on this, all right? Okay, so this is the use case, and this is probably one of the biggest use cases for Apache content getting mislabeled. It's either created in the /temp directory and /root, /home directory. I'm happy with it. I run a Firefox. Now I want to move it into production, and I forget to fix the SELinux labels. So I get that. So I check the permissions. I already went through this. SELinux sucks. Okay. So what I can do after I move the object into the place is I can run restoreCon, because restoreCon is going to look at the past and force everything to be the way SELinux likes underneath that directory. Yes. If a confined root user, first of all, SELinux knows nothing about the root user. It's a label on a process. If a label, as I showed you in the OpenShift example, that was the root user trying to cat Etsy Shadow, but because it was labeled as OpenShift T, it's not allowed. Right? So root means nothing. Root is a discretionary access control, not an SELinux issue. So move preserves labels. There's a move in rel 7 now there is a move capital Z. And what that does is almost everybody that uses move with SELinux expects it to do the restore con for you. So now we have a move minus Z, which will relabel the content for you. Okay? Right? Okay. So if you do this, which I have on my system, suddenly things start to work much better. The NSA hates the idea of this. Okay? Not the discretionary, but if you think about a top secret, if I move a file around the operating system and all of a sudden it goes from top secret to unclassified, that's a problem. Okay? But for targeted system, it makes some sense. You know, for the systems that most everybody uses, it makes a lot of sense. That's why we can never change the default to be minus Z, but you can change it yourself. Not a common problem. My machine's labeling is so wrong it will not boot. Okay? So there's a kernel parameter you can use called enforcing equals 0. Okay? It's different than SELinux equals 0. If you boot a machine with SELinux equals 0 because you think SELinux is screwing up your system, that will disable SELinux. But SELinux, or the operating system, is smart enough to know that you booted without SELinux. So what it's going to do, it's going to put a little file, /.auto-relabel, and the next time you boot with SELinux, it's going to relabel everything because it has no idea what you created while you were logged in without SELinux. So it forces a relabel. If you boot with enforcing equals 0, that means that the system is running in permissive mode, the equivalent of set enforce 0. So the labels will continue to get created correctly, but SELinux will not block anything. Touch auto reboot will relabel the entire system. And if you have the example you were using where you have 8 million billion files there, a mail server type thing, go get lunch. Okay? Because it's going to walk through the entire file system, looking at every single inode and checking to fix the inodes. Usually on a modern system, it probably takes 5 to 10 minutes on a normal laptop, but on massive systems, it can take massive amount of time. So brace yourselves. How do processes get on labels? SELinux implements process transitions. I can write a rule and policy that says when process labeled A executes a file labeled B exec T, the kernel will transition the process to B_T. So I'll give you an example. When the init system, which is running as init T, runs Apache, which is labeled as HTTPD exec T, it will run it as HTTPD T_T. So that's how transitions work. That's how processes get their labels. So domain audit, so it's a rule that looks like that. Look what happens at boot. Okay, so this is a fairly old slide, doesn't even cover systemd, but when a system boots up with SELinux, the first thing that system does when it comes up, this is somewhat of a lie because there's no SELinux when a machine boots up. So the machine's booting up, it's going to read in the SELinux policy off the file system, and what the policy says, any process on the system, by default, at the point that it reads in the policy is going to be kernel_T. The policy has a rule that says if kernel T executes an init program labeled init exec T, it will run that process as init T. So kernel T runs systemd. Systemd is labeled this. It runs as init T. Now we go down, and it runs an init script, which is labeled init_rc exec T, transitions to init_rct. That goes down and runs klog exec T, which transitions to klog exec T, or init named D exec T. So obviously this is a rel 6 system because systemd works a little bit differently, but not too much differently. Similarly, you get down to getty running, gets down to login, at which point the login stuff works a little weird. So login program has SELinux knowledge in it. So the login program is going to figure out what to log in the user in. So it has SELinux. So it picks the labels that the login in. But this basically is how all the processes get on the system. Most processes you exec stay in your context. So if you're running as unconfined T and you execute a program, it's probably going to stay as unconfined T. But we've written policy that you can be running as a user T, you execute Firefox, and it'll go run in Firefox T. So we have that type of transitions for user space. How files get created on creation. So two things that happen. We've told you how they get initially labeled via RPM and the file context files and restorecon, and we told you how processes get labels. Now we're talking about an administrator or some object on the system is creating new content. How does that get labeled? Multiple ways. The first way is a file gets created based on its parent directory. So if you create a file inside of a directory labeled etc, by default it will get created as etc. If a tool like SELinux is SELinux aware, it can override that. So RPM, for example, tells the kernel, I'm about to create an object, please create it with this label. RestoreCon changes it. For example, password creates two contents when it creates objects on the system. It creates etc password and etc shadow, so it's going to create these with different labels. So a password has to have SELinux awareness in it. Policy writers can write rules to do what we call file creation transitions. And this basically means when a process is labeled Network Manager T and it creates a file in a directory labeled etc, we want it to create it as netconf T. So that means when Network Manager creates etcresolve.conf, it creates it with a label of netconf T instead of being etc. So we can write all these rules into policy, and we can do, this is what the policy will look like. Network Manager T creating etc, we'll label as netconf T and create it as a file. So there's a fourth one that just came. This is only in RHEL 7, not in RHEL 6, and this is actually a huge advantage to usability in RHEL 7 versus RHEL 6. We can write rules that says when you create a file and we can do a transition based on the name of the file, not the path of the file. Path means nothing to the Linux kernel. Names of file objects mean something. Paths mean nothing. So I can write a rule that says when an unconfined T process creates a directory in a user home dir, which is your home directory label, I want to create it as SSH home T only if it's named .ssh. So one of the biggest bugs that we get for RHEL 6 and RHEL 5 is admins set up a brand new SELinux system. They go into root/.ssh, they create the root.ssh directory, and all of a sudden they try to set up public key automatic logins, and it blows up because the SSH daemon is not able to read content in the root home directory because they have to run RestoreCon. This actually fixes that problem. So we have hundreds of these rules. So if sysadmins go on creating random content that we know about, we're going to label it. So if he creates etcresolve.conf, we label it correctly. So we can set up all these rules. It also, we actually have patents on this to improve security of the system because we can actually tighten up some of these file transition rules. Okay, I've just beaten the living hell out of labeling, okay, but there's a hell of a lot more. If we really wanted to go through it, we could go over 3 days. But basically, all this stuff should work, and everything I've talked about up to this point is, if you picked up one thing, it's RestoreCon and the SEManage command. Those are the two most important things we just covered. We gave you a little more insight of what's going on in the system. Section 2 is you change the system defaults but did not tell SELinux about it. SELinux needs to know. These are, when we write policy, if I write policy to just allow Apache to work, I end up writing unconfined T, right? Because Apache can be configured in 4,000 different ways. Things like FTP. I set up an FTP server. I want FTP server to share var FTP to the internet. Okay, someone else wants to use FTP to be able to share home directory content to the internet. Someone else uses FTP and they want to share everything on the system to the internet. So how should I set up the default policy for the FTP daemon? All right, so we introduced many, many years ago the idea of booleans. So that allows a policy writer to write these booleans or if-then-else rules into policy and allows an administrator to toggle it a little bit. So booleans are if-then-else rules written into policy. If you want Apache to send mail, you can do that command. How many people here set up their Apache service to send mail? Good. Very few of you. Okay? The default is that it's not allowed to. Why is that? Bash exploit happens, all of a sudden you become a spam bot. Okay? So out of the box, you would expect your Apache servers not to be able to send mail, except for the two guys in the room who wanted to send mail, and they're going to say SELinux sucks. Okay? Okay, or disable, right? They're going to do 740 and disable SELinux, get the hell out of my way. Okay? So we have the booleans to do that. If you want to use it to use FTP to access this home directory, you can set a boolean that says FTP home dir T. How do I know about the booleans that are available or the file context? So SEManage boolean list will show you all the booleans. We actually have in RHEL 7, there's over 1,000 man pages Every single confined domain in the system has an underscore SELinux after it. So it's not bad to do man k SELinux and then grep for some string. So if you wanted to look up a man httpd underscore SELinux. By the way, I didn't write 1,000 man pages, okay? So these are all auto-generated, but it does an incredibly good job of that. And this thing will cover all the stuff like what are the booleans available for the Apache daemon, what are the types available for the Apache daemon. So there are lots and lots of man pages to help you out. There's a tool called Troubleshoot, which runs usually runs on desktops. Anybody that's played with the Linux desktop, Fedora desktop, has seen Troubleshoot. Troubleshoot, I used to say, is Dan's brain in a box, right? So it basically looks at an AVC and tries to analyze it and then gives you a response that says, hey, it looks like Apache's trying to send mail. You might want to turn this boolean on, okay, if it wants to send mail. If you don't want Apache to send mail on, you're being hacked, okay? I don't put that part in, so I hope people just don't read this and say, oh, I didn't know my Apache wanted to send mail. Let me still send mail. There's a tool, Auto to Allow, that we're going to cover in a little bit. Auto to Allow basically can analyze your log errors. So SELinux errors go into the audit log system by default. They're also now in RHEL 7. They're going into, I think in RHEL 7, at least in Fedora now, they go into the journal as well as the audit log. So if you run Auto to Allow to look at what happened on your system, Auto to Allow will give you a message that says, here's the rule you'd want to add to your policy, but hey, there's 2 booleans available to allow you to allow this access. Using Auto to Allow to diagnose issues when Apache is running passenger, you end up with something that looks like this. So if you wanted to run passenger, you can get these booleans and turn them on. Problem solved. You didn't change the system defaults, but you changed the system defaults, but you didn't tell SELinux about it. SELinux needs to know. SELinux also controls port types. So we basically say Apache's only able to listen to port 80. SSH daemon's only allowed to listen to port 22. I never remember what. So out of the box, if I see an Apache web server trying to listen to port 492, or Apache or SSH daemon trying to listen to some random port, SELinux is going to block it, going to report an error and say, hey, something strange going on in the system. So I want SSH daemon to listen to port 55. SEManage port is the tool you're allowed to change that. And this basically says treat port 55 as if it was the SSH port. How do I tell what ports are available? Well, man SSH daemon underscore SELinux will tell you all the port types that are available. There's also an SEManage port list, which will tell you a huge amount of ports. Port prefix usually matches the type associated with, so anybody guess what HTTPD underscore T's port type is? HTTPD underscore port underscore T, okay? So in RHEL 7, SE Policy Network is very handy. That shows you stuff like this. SE Policy Network, there's basically tools to analyze the policy. It tells me which port is assigned to SSH port T. And if I want to know all the stuff about the SSH daemon T as far as networks is concerned, these are all the ports that are allowed. It shows you some Boolean information, so there's lots of information available. So those are the 2 things. So 2 major causes of SELinux labeling issues. The second one is you change some configs. Change some normal config, and SELinux needs to be told about it. The next one is SELinux errors. Okay, SELinux and application errors. Over the years, as we've evolved, RHEL 4 we had a ton of errors. RHEL 5 we had less errors. RHEL 6 we got better. RHEL 7 we got better. We're always getting better at figuring out these because we've been running SELinux since Fedora 3, and now we're on Fedora 23. So we've been doing this for 20 versions of Fedora. So SELinux policy can have bugs, unusual code paths, configurations that we never tried, redirection of standard out. So SELinux, all we can do with SELinux is run an application under a confined domain and then wait to see what blows up. Okay, so we learn over time. It's like doing static code analysis. We can do a little bit of that, but you really need to run these things in the wild to figure out all the things that an application is able to do in the system. And then we write rules about that. Applications are SELinux bugs that have been not fixed yet. Applications have bugs. Everybody know what a leaked file descriptor is? So 30 years ago, when they were developing the C language, they decided that when I did a fork exec, I want standard out, standard error, and standard in to be leaked to the new process. So when I do a fork, all the open file descriptors in my original process get inherited by the child process. you know that it's not just 0, 1, and 2 that get inherited. It's, you got a network socket open, it'll get inherited by the child process. Every single process that now becomes a child, grandchild, on down has full access to that process. When we first started using SELinux many years ago, we found the init system was leaking dev init control. That's the socket that you're able to send a packet to change the run level of the system. So every process on the system had full access to that unless an intervening process went through and closed all file descriptors. So we were finding all these domains that basically could change the run level in the system. No other system in the world would figure that out except for SELinux. But anybody that writes code, every single developer in this room that writes code probably never thinks to close the file descriptor before an exec. So there are calls that you can basically say, this file descriptor I want it closed when anybody execs out of here. But you have to code that way. Okay? So we found hundreds of those. Executable memory, this is basically buffer overflow attacks. SELinux will block those, but a lot of code is badly written. Badly built libraries cause these problems. Report bugs to Bugzilla. If you find them, we will fix them. Applications or SELinux have bugs. You can tell SELinux to just allow those using to auto to allow. So SELinux is blocking PostgreSQL. Did you make the labeling correct? Yes. Did you make sure there were no appropriate booleans? Yes. Most important thing you're going to learn today, or the most abused thing you're going to learn today. How do you use auto to allow to build policy? So use auto to allow to build your own custom policy module. If SELinux blocks something on PostgreSQL, you can go through audit to allow. You can go through your audit logs, pipe it to audit to allow, give it a -m, and tell it to create my PostgreSQL.pp policy package. Then you can install the policy package. This basically says, SELinux, shut the hell up and let me do what I want to do. Okay? The problem with this is if you do this all the time, you're allowing the hacker to do anything he wants. So you really should look at what you're doing here, understand it, but if you just want to if you don't want to set, this is better than setting force 0. It's much better than disable SELinux, but it allows you to get by. But when this happens, you should really look at what you're adding. Try to figure out what you're adding for rules. Make sure you're not allowing too much, and you can always ask for help. There's lots and lots of people on the internet that will help you with your SELinux issues. You can even send me email. Report the bug to your TAM, your support, your Bugzilla, mailing list somewhere. Report it so we can find it and fix it if it becomes a bug. So the big one. So all of a sudden we have shell shock. We have your Apache web service trying to set enforce 0 on the system. Okay, might be something we want to investigate. You probably don't want to do a set enforce 0 audit to allow. Let the bash CGI script turn SELinux off. So if you have a confined domain that tries to load a kernel module, turn off SELinux enforcing mode, write to Etsy, or write to ShadowT, modify IP tables rules, you might be compromised. The problem is the tooling really can't tell the difference. So SE Troubleshoot tries to do a good job of looking for these known signatures of attack vector, like disable SELinux, and figure no confined domain is ever going to be allowed to disable SELinux. So those are good things to watch for. So SE Troubleshoot has a few diagnosis tools, but SE Troubleshoot and SELinux is not an intrusion detection tool. All it is protecting you in case you had a vulnerability. Questions? By the way, there's more slides after this if we have time. Yes?
So I was wondering if you could go over the difference between going in as a non-root user and escalating to root and attempting to do things
Right.
being blocked versus having console-based access to the box, logging in as root, which is not disabled, and then just do set enforce off, and then I can whatever I want.
Okay, so all right, the question is, he's asking about confined users. So I didn't really cover confined users here. On most systems, by default, the user that logs into the system is unconfined T. Okay, that basically means he basically has allow ***:**. Okay, that's the rules for the unconfined user. So if you have a user that logs into the system as root, he has full access to the system. He logs in your home directory, you have full access to the system. You go through sudo, become root, you can do anything you want. That is the default unconfined user on the system. I think we have a couple slides in the next section that might cover confined users. We can control the user process. The problem is if I controlled the user process out of the box, we would have everybody disabling SELinux because nobody as an administrator wants to be confined, okay? I actually run confined, so I run a staff T, and the staff T, the only way a staff T user can become root is actually through sudo, and I have a transition rule through sudo that can allow me to become administrator, at which point I become unconfined T. There's actually even tighter things called sysadmin T that are used in like MLS systems. I have policy, remember I showed a picture, I confine my wife with SELinux, she runs a thing called xguest. She has no reason to ever connect to random ports. All she does is use the web browser to get onto the internet. So I can actually control that she can only connect to the network, the Firefox type ports. She can't run sudo, there's no way. So if she downloads an application that tries to run sudo, SELinux will block it. Same thing with my parents. My parents run in the xguest mode. Basically, it's a user that can log into a box and do very little. There's even a tighter policy called guest T, which is basically for SSH accounts. If you have an SSH account in your system that you allow hundreds of users to log into, you really want to put those guys in a box so that you don't want them leaving the network. When I do the longer talks, I call it the Hotel California. You can come in anytime you want, but you can't leave, okay? So it basically controls, who's able to log on. You're able to log in the box, but you can't SSH off of the box. And these are for like web services, right? So my content, ftp.redhat.com, fedora.people.redhat.com, they give me an SSH account so I can update my public HTML, but they don't want me running sudo and all these tools to try to become root on the system, so if I could lock those down with SELinux. So I have the capabilities to do that, but SELinux is more about, by default, is more about controlling network-facing services rather than users that log into the system. You can enable the loggers using the system, but that's more of an advanced SELinux thing. You can do a really nice job, too, of controlling sudo. Okay, so you can actually have a confined staff T user, and you could set up a user that can execute a shell script as root, and then write policy on that process to control it. Yes. Yes. Yeah. I mean, you could build some kind of system if you cut off certain categories and treated those differently, but yeah, pretty much no one to my knowledge has combined them. Yes. How do I handle nested virtual? Well, SELinux can run in the container, switch, not containers. It can run in the VMs at separate policies. So you can run a RHEL 6 box with a RHEL 6 policy on top of a RHEL 7 as long as you're using KVM for virtualization. If you're running inside of containers, we basically we don't disable SELinux inside. We lie inside of the container that SELinux is enabled because we don't want any process inside of the container accidentally attempting to do SELinux actions. So if you're inside of a container, if you did a get enforce, it'll say disabled. If you get outside the container, same process in the system, it will be in enforcing mode. So in containers, we only have one policy. So and my rule about containers is what happens in Vegas stays in Vegas, okay? So we allow you to do anything you want inside of your container, but you're not allowed to break out of the container. And we use the SVIRT MCS. That's basically how OpenShift works too. But yeah, you can, as long as you can use full KVM virtualization, separate kernels, then you can have separate policies for each object. Anybody else? Yep. Yeah, there's been some. There has been some effort to get Fuse to work over the years, and there is effort like NFS. So Fuse file system. There's certain file systems that don't support XAddrs properly to be able to handle it. So NFS for years didn't support it, and basically with an SELinux system, you basically label the entire mount point with a single label. So NFS by default is NFST. NFS now, if you use RHEL 7 clients and servers, and hopefully soon NetApp and other services will support. NFS protocol now supports it, just a matter of getting the services, all the clients and servers to start supporting XAddrs. Fuse has the same type of problem, and Fuse has some weird situations that have never quite been fixed. Anybody using a Samsung phone? Okay, anybody using the Nexus? This is a Nexus phone. You guys disable SELinux on this? Did you know SELinux is on it? Okay, so SE Android. Why is SE Android easier than SELinux on a RHEL box? Why is it able to confine it easier? Anybody have any idea? Remember the canonical talk yesterday? The amoebas, right? The amoeba applications crawling all over each other, right? FTP being able to do 15 different configurations and all this weird configuration stuff that's happening. When I'm using an app on top of one of these phones, what is it? It's a box, as Spaceman was saying yesterday. Okay, in our terms, we call them containers. So when we move to containers, SELinux becomes a lot better because I can treat every single container as the same object. I no longer have to worry about these random directories and random way you set up things. So SELinux on top of virtual machines, on top of containers, almost becomes second nature. Anybody that disables SELinux on Docker, you are out of your friggin' mind, okay? Okay, especially if you're running, a fellow coworker of mine calls Docker is all about downloading random shit off the internet and running as root on your system, okay? And that's really what it is, right? Because you're just going and grabbing random content and you put it in a container and you're giving it root. And there's very little separation. There's some separation. I do a much longer talk on that was rejected for here on Docker security, but SELinux provides the best file system separation, again, because it can basically say you are a container process running on a system. If you try to read database data, you're not going to be allowed. You try to read Shadow, you're not going to be allowed. Basically, what happens in Vegas stays in Vegas. You try to break out of Vegas, SELinux is going to shut you down. Okay? And because it's all built into the system, it's built into Docker, the only time you have to worry about labeling is if you volume mount into it. And there's a colon Z, lowercase z, and a colon uppercase Z, which actually will fix the labels of whatever you stick. If you volume mount into a Docker container, it will fix the SELinux label of whatever you volume mount in. Yes, someone back of the room. Yep. No, because SELinux is not a mechanism for getting around discretionary access control or other types. Right, security is always in depth. Right, you always want, you know, when I run Docker, I have read-only file mounts, I have discretionary access control drops, I have capability drops, I have SELinux drops, I have seccomp. I want all these things. What I don't want is one of them installed that bypasses the other ones. So you have to configure everything. So we're not giving you backdoors with SELinux. So in order to become root on a system, if you're a confined application, you have to not only change your label, SELinux label, to do stuff, but you also have to change through sudo to become root, UID 0. So that's different. There's no bypass. There's no secret SELinux bypass mode to bypass things like discretionary access control. Are we running out of time? Yeah.
Can you give a best practice for using live fuse?
No.
There's no solution for it?
To use live fuse?
I'm sorry.
LibFuse? I don't know what that does.
I'm sorry, I'm mixing. Like, instead of NFS, we're using fuse.
Yeah, I don't know fuse, so.
Like, did you use S3FS?
No. I just work on the files. Okay, I'm going to upload all these slides. I think we're totally out of time now. The second part of this talk covers how to manage SELinux in a distributed environment, and which is really critical. And we don't, again, this talk could take 3 days if we wanted to go through it all. But the main idea is you configure. A lot of people go on and you configure one machine the way you want it. All right, so you go out and you do all your SEManage commands, you do all that. SEManage commands also have the ability to extract your configuration, all your SELinux configuration into a flat file. You can then move that flat file to another machine and load it. Okay, and what that will do is basically take all your booleans, all your file context changes, any port changes, things like that. So if you configured one Apache server the way you want it, and you want to duplicate that Apache server on 100 machines, you can do that with these tools. Lastly, about SELinux, again, this covers it. The question we've often gotten asked about SELinux: don't we have some magical tool that makes managing SELinux easy? And I always say, yes, we do. We have lots of them. They're called Puppet, Ansible, CF Engine, okay? Whatever SELinux is configuration data. It happens to be security configuration data, but it's configuration data on your system. If you manage your systems using satellite with RPMs, you can package SELinux and satellites on RPMs. If you manage using Ansible, great idea. We now own them. You can do it with Puppet. You can do it with other tools, okay? So managing SELinux in the enterprise the way that Fedora does it, the way that OpenShift does it. They use Ansible to manage all hundreds to thousands of machines using standard tools, okay? Thank you for coming. And did the Patriots lose?